So let's take a look at how the second law of thermodynamics plays out when we look at a simple calorimetry problem. So here what I'm going to do is I'm going to start with two containers. Each of them hold 1 kilogram of water. In one of those containers, the water is at 40 degrees Celsius. In the other, it's at 60 degrees Celsius. I'm going to combine those into a single calorimeter, and I know that at the end, I'm going to end up with 20 kilograms of water that reaches thermal equilibrium at a temperature of 50 degrees Celsius. So in terms of the schematic and the table that we usually set up for this kind of problem, again, I've got my cold stuff over here starting at 40 degrees Celsius, my hot stuff over here at 60 degrees Celsius. There's going to be two processes where energy is exchanged as heat. I'm going to label this one Q1, this one Q2. And again, when I go through and think about each of these steps, well, for Q1, temperature is clearly changing, so it's a specific heat process. This is the cold water taking in energy to reach a warmer temperature. So it's got to take in energy as heat, and therefore Q will be a positive quantity. The mass that goes into this specific heat calculation will be the mass involved in Q1, which will just be 1 kilograms. And again, it's changing its temperature as water, so I need the specific heat of water. For Q2, same thing, it's changing its temperature. It's simply decreasing its temperature because it's giving energy up as heat, therefore I need a minus sign. Mass 2 is also going to be 1 kilograms, and again I need the specific heat of water. This is all information that we would have put together in terms of solving the conservation of energy problem that told us what the final state was. This is our first law of thermodynamics problem that's giving us this answer. To see how the second law of thermodynamics plays out with this, well, what I want to do is I want to calculate the total entropy change for the system. And since I have two processes that my system undergoes, I simply need to calculate the entropy change along each process. I know that both of my processes are specific heat processes. That tells me which delta S equation I want. So in this case it says I want that the entropy change moving from state A to state B is equal to plus or minus, where again the sign I know, mass times specific heat value times the natural log of some temperatures. And again I look at this and say the signs I have, the masses I already know, the specific heat values I know which ones to plug in. So these first three things are already taken care of in this equation. I know the temperatures, but I want to make sure, of course, that I plug those in Kelvin. So in terms of calculating out the entropy change for my system, I'm going to use that term twice, plus M1 times the specific heat of water times the natural log of the hot temperature over the cold temperature for process 1, minus mass 2 times the specific heat of water times the natural log of hot temperature over cold temperature for process 2. And again, needing those values in Kelvin, 40 degrees Celsius is 313 Kelvin, 50 degrees Celsius is 323 Kelvin, 60 degrees Celsius is 333 Kelvin. And so if I'm looking at step 1, the hot temperature was the final temperature of 323, the cold temperature was the initial temperature of 313. For process 2, the hot temperature was the initial temperature of 333, the cold temperature was the final temperature of 323, and so I know everything to plug in. Here I'm going to choose to use my specific heat values in joules per kilogram Kelvin rather than kilojoules per kilogram Kelvin, which is why this is 4186 rather than 4.186. I've done that for both of them, and largely that's just because I end up with a pretty small value of 4.01 joules per Kelvin. So calculating out the entropy change, relatively straightforward. Get yourself the right equation, which type of process is going to tell you which equation you need, and then the sign, mass, value. The only detail really worth emphasizing is just make sure you get your temperatures converted into Kelvin before you go plug them into the equation. So is our calculation of the entropy change for the system consistent with the second law of thermodynamics? We calculated out a positive value for the entropy change for the system. What the second law of thermodynamics told us was that the entropy change for your system will be positive if you have an irreversible process. So that begs the question, is this an irreversible process or not? One way to think about this is simply, well, have you ever seen 2 kilograms of water at 50 degrees Celsius spontaneously separate into 1 kilogram of water at 60 degrees Celsius and 1 kilogram of water at 40 degrees Celsius? The answer to that question is obviously no. You've never seen that happen spontaneously. If that was going to happen, you had to do work on your system. You had to change what was going on with the energy so that you heated up some amount of water and cooled down the rest. What this is hinting at is the fact that thinking about how the entropy of our system changes is very intimately related to how we expect things to proceed in time. So this is what's known as time's arrow in terms of thinking about entropy. Largely what this means is that if I showed you the video of something, odds are pretty good that for most processes you could figure out whether or not that video was running forward or backwards based on whether or not that was something you expected to happen or not. So if I showed you a video, and I get that this would be an incredibly boring video, but let's say I showed you a video of a glass of ice that I've set out on the counter. You're not going to watch much, but over the 20 minutes or so that it's sitting there, what you would watch would be that the ice would eventually melt. All of it would become water. It would end up warming up to a final temperature of room temperature. If I showed you a second video that said, hey, here's a glass of water at room temperature, and what you watch over 20 minutes is that water that seems to spontaneously be cooling, and then spontaneously, for no reason that you can see in the video, that cool water at the freezing point freezes and turns into ice, you would recognize that something's wrong. As a concept, entropy is intimately related to how we expect processes to occur. Why we expect things to happen in a certain order is very much a function of entropy. To emphasize this, well, let's come back and ask the question, so why can't the change in entropy for your system be negative for a closed system? Why do we have to have something that's greater than or equal to zero? To keep the calculation simple, instead of thinking about this entire process or this entire process where clearly the temperature changes, let's think about some tiny little fraction of it where energy is exchanged from the hot stuff over here to the cold stuff over here. But basically that's such a small transfer of energy that I can effectively think of that happening at a constant temperature. The energy for my cold stuff as it's warming up, that's going to be positive. It's taking energy in. The hot stuff as it's cooling down, that energy transfer as heat is going to be negative. But those two things are equal in amount. One of them simply positive, the other one's negative. The nice thing about thinking about this tiny little exchange of energy where I can think about the temperature being constant, of course, is that it gives me an easy expression for calculating out what the entropy change is. So the entropy change over this tiny little exchange of energy is going to be this Q value divided by the temperature at which it happens. And so I know that for the cold stuff, when it takes that energy in, because the Q is positive, the entropy change is going to be positive. For the hot stuff, as it gives energy up, because Q is negative, the entropy change will be negative. The absolute values of these Q's are the same, but these temperatures are not. And so because this high temperature, the hotter temperature, is larger than the colder temperature, that means when you take the same thing and divide it by these two temperatures, the one where you divide it by the smaller temperature gives you something bigger at the end. The entropy change that happened at the colder temperature is going to be larger than the entropy change that happened at the hotter temperature. The entropy change that you know is positive always has to be greater than the entropy change that you know is going to be negative. So saying that the entropy change for a closed system can never be negative is another way of saying that the energy always is spontaneously transferred as heat from hotter objects to colder objects and never the other way around. So you can think of this as, again, a reformulation of the second law of thermodynamics. And why this occurs is simply that in the energy being exchanged in this way, there are more possible ways that the energy can arrange itself when all of the water ends up at 50 degrees Celsius than what it can in the initial condition where half of it's at 40 degrees Celsius and half of it's at 60 degrees Celsius, or at any point in between. Finishing up here, what our system has done is it's maximized its possible entropy.